The second derivative test in one dimension is fairly intuitive. If the function has zero slope and it is concave up, then it is a minimum. And if it's concave down, then it's a maximum. And if the concavity is zero, then anything goes, and the behavior is determined by higher order derivatives. Now, in two dimensions, we learned in school that this funny looking formula tells us something about the concavity. In this video, we will explore the full geometric intuition behind the formula. Then, we can build a generalization of the formula to higher dimensions. Now, the real interesting question is, what does the second derivative test have anything to do with why concrete or bones tend to fracture diagonally, or how correlation between statistical quantities work, and the mathematical description of the rotation of a rigid body? Let's start with the two-dimensional function and choose a point on it. Unsurprisingly, the zeroth order Taylor expansion at this point simply gives the function's value. Slightly more interesting is the first order expansion, which involves the partial derivatives with respect to each coordinate direction. Geometrically, the first order polynomial represents the tangent plane, much like the tangent line in one-dimensional case. We're about to get really cluttered here, so let's use bold letters to represent vectors. Then, the tangent plane, or the first order expansion, is given by this formula. Now, for the second derivative test to be meaningful, we need both partials to be zero. Now, much like in one dimension, the second order expansion in two dimension is the tangent paraboloid at the point. And it depends on each of the second derivatives. If you are wondering why the mixed partial term isn't divided by 2 factorial, unlike fxx and fyy, it technically is divided by 2. Just there are 2 equal copies of them due to commutativity of partial derivatives. Now, just like how the gradient captures all the information about first derivatives, the second gradient captures all the information about second derivatives. This matrix is also called the Hessian. If you want to continue to third derivatives, it becomes a rank 3 tensor, so it does become increasingly disgusting to work with. But luckily for us, all we need is the information about second derivatives. Zeroth order term just affects the height, and the first order terms all have to be zero for second derivative test to be meaningful. So we really only need to study the second order expansion, or equivalently, the second partial derivatives. Let's label the Hessian matrix as H. The Hessian does indeed provide a complete picture of the function's concavity, but it's quite unintuitive on its own, so we typically extract two important scalar quantities, the determinant and the trace of the matrix. The determinant is precisely the discriminant for the second derivative test. And the trace, if you're not familiar with it, is the sum of the diagonal entries, which in this case is the Laplacian. We will eventually understand what these quantities represent. We mentioned earlier that we only need to consider the second order expansion. If both directional concavity is non-zero and with no mixed terms, there are just 3 possible cases. Either it's concave up in both directions, or concave down, or it has both up and down, so it makes a saddle shape. Now, in this case, the determinant simply is the product of each directional concavity. If they have the same sign, it's a maximum or a minimum, and if they have different signs, it's a saddle. To determine whether it's actually a maximum or a minimum, we could use the Laplacian for the first two, which is twice the average concavity. But unlike using just one of the second derivatives, as most textbooks teach, the Laplacian gives us a meaningful geometric information even for the third case. Since the Laplacian is positive, that means on average, the saddle curves upward more than downward. So we have just started scratching the surface on what these two geometrically mean. We will go into much more detail later. Now, if one of the directional concavity is zero, the second derivative test becomes useless. All 3 of these functions have no y-squared term, so the behavior in y direction is dominated by higher order polynomials. For the first one, it looks like a parabola in x direction and a line in y direction, so it looks like a half pipe. For the second one, it looks like a cubic curve in y direction. And for the third one, it looks like a quartic curve in y direction. So anything goes. It could be an extremum or a more complicated higher order saddle-like shape. The second derivative is inconclusive, and the local behavior depends on higher order terms, so we will not look at any of these cases anymore. Now, back to non-indeterminate cases. We know all about these diagonal ones, and we eventually want to know what's going on with these ones with mixed terms. So first, let's backtrack a little and analyze the diagonal case a little more. This function is most concave along the y direction and the least concave in x direction. Maybe it's easier to see if we draw in some level curves at several different heights of the function. Since the elliptic level curves are the shortest along the y-axis, we can see that it is the most curved in that direction, and the opposite for x-axis. Analysis becomes even more obvious if we consider a case where one of them is negative. If we take a look at the directional concavities in all directions, the function is most concave up along the x-axis and the most concave down along y-axis. And since the maximal and minimal concavities have opposite signs, there are directions with zero directional concavity, guaranteed by the intermediate value theorem. Now, how do we actually compute these directional concavities? Well, the directional derivative along any direction can be expressed as a linear combination of partial derivatives in x and y direction. Then, the directional concavity is simply the second directional derivative. And if you need to take a mixed directional second derivative along any two directions, you can take them in whichever order. Now, could we try working with the rotated coordinate system? Let's try 30 degrees first. We can compute the new Hessian in this coordinate system using directional second derivatives. And using these values, we can reconstruct the second order expansion in this coordinate. That's what we were looking for in the first place. These mixed terms correspond to some rotation. And maybe we could try computing the Hessian for one more coordinate system. So let's try 45 degrees, where the directional concavities were flat along the diagonals. Now, the Hessian in each rotated coordinate system looks different, but the determinant and the Laplacian is the same. So, it's good time to update these notions. The determinant represents the product of the maximal and minimal directional concavities, while the Laplacian is twice the average of them. Now, if we start with these cases that have middle terms, they must be paraboloids aligned in some different directions. And these special directions are called principal axes. Here's a little Desmos demo on how changing the middle parameter would alter the shape. I left a link in the description so you can play around with it yourself. So, we have answered all the important questions. This quadratic function is some rotated paraboloid, and the determinant is the product of the principal concavities. Perhaps the next big question we can ask is, how much should you rotate to align it with the principal axes? As per a brute force elementary proof, you can open your pre-calculus textbook and go to the chapter about rotated conic sections. Cotangent of twice the angle we would have to rotate is equal to a minus c divided by b. To summarize the proof, we substitute x and y with new variables in the rotated coordinate system. Then find the angle that would make the middle term disappear in this new coordinate. But this elementary proof is quite uninteresting on its own and doesn't provide any geometric insight. As per an elegant algebraic proof, we need an entire semester worth of linear algebra. So we're kinda stuck between a rock and a hard place. For now, let's build a very rough intuition. So let's start with the circle, which can be described using vectors pointing in every direction. If we apply a linear transformation corresponding to a symmetric matrix, then the circle would elongate to an ellipse and most vectors are thrown out of their original direction. But there are exactly two perpendicular axes where the vector is influenced only in its own direction. And those are called the eigenvectors of the transformation. And they happen to be orthogonal since the transformation was symmetric. Now, why the principal axes of the Hessian happen to align with the eigenvectors is a much more subtle question. For now, let's just accept it and come back to it later. So, whichever technique you use, the cotangent formula or eigenvectors, you can always reorient yourself to principal directions. Now, what about in 3 dimensions? If this happens to be a maximum or a minimum, then the level surfaces are elliptic. And if it's a saddle, then it's hyperbolic. And the mixed terms contribute to rotation. Can we use the determinant and the trace as a second derivative test? In this very specific case, yes, but in general, no. Of course, the best geometric description comes from the principal axes. And all the principal concavities must be positive for the point to be a minimum, or negative for it to be a maximum. But this one has a mixed signature, so it's a saddle. Now, just like before, the determinant is the product of the principal concavities, and the trace is the sum. And since the determinant is negative, we could deduce that either one or three of them are negative. But the sum of them are positive, so it's impossible for all three of them to be negative. But in general, two equations cannot determine three variables, so the determinant and trace cannot reliably be used as a second derivative test. Suppose we have a symmetric matrix of any dimension. Then theoretically, it can always be rotated to align with its principal axes. If each lambda is positive, then we say the matrix is positive definite. The lambdas, which are the principal concavities of the Hessian, are called the eigenvalues of the matrix in a more general linear algebra context. Now, the algorithm that is directly analogous to the second derivative test is to check if the determinants of each upper left submatrix are all positive. And if they are, then the matrix is positive definite, so we get a minimum. To check for the negative definite case, the signs of the subdeterminants start negative, then alternate. Although, in my opinion, the better way is to check if the negative of the matrix is just positive definite, since the negative of a downward paraboloid is just an upward paraboloid. This algorithm is called Sylvester's criterion, but it becomes incredibly inefficient as the dimension increases. If you have ever computed the determinant of a 4x4 or 5x5 matrix, you know how miserable it is. So there are much better algorithms out there, such as Cholesky decomposition, that can check for positive definiteness more efficiently without calculating determinants. Now, to actually determine the principal axes or principal concavities for higher dimensional cases, that's a whole nother level. Computational and numerical linear algebra is an active field of research, so mathematicians and computer scientists are still working to make better algorithms. Linear algebra is a subject where the theory and abstraction is much easier than the computation. So it's actually not too hard to prove that a quadratic function in any dimension can be rotated to align with its principal axes, but actually computing them is a nightmare. So if your goal simply is to find all the local minima and maxima, second derivative tests in high dimensions isn't the most practical. For example, there is a test that only involves first derivatives. We could sample some points in the neighborhood around each critical point, then let each point walk toward the steepest upward direction. If the point is a local maximum, all the neighboring points will climb toward the peak. And similarly, we can make each neighboring point descend in the steepest direction. So for a minimum, all the neighboring points will converge toward the lowest point. This is the gradient ascent and gradient descent algorithm. And for large dimensions, this would be significantly cheaper to compute than the second derivative test. So the second derivative test kinda sucks for sufficiently high dimensions, but the mathematical insight we have gained along the way is invaluable. For example, suppose we have a piece of solid, then we can chop it up into infinitesimally small regions. Let's focus on a single piece to analyze the stress. Along the x-axis, the material could be experiencing some internal tension or compression, and the stress on the left and right faces must be equal and opposite. We can call this component of stress sigma xx for a stress along the x-axis in the direction of x-axis. And we could think of similar tensile or compressive stress in y direction. Now, there are off-diagonal terms for shear stress in x direction toward y direction and y direction toward x direction. This is called the Cauchy stress tensor, and it is a symmetric matrix. As for why it is symmetric, if the xy and yx terms are different, then the piece would be spinning. Suppose that this piece is experiencing 1 unit of pure shear in each direction. If you rotate your coordinates to principal axes, then this can be turned into pure tension and compression. The underlying mathematics behind the transformation of the stress tensor is identical to that of the Hessian, or for that matter, any symmetric rank 2 tensor. Here is a page from a typical engineering textbook on a solid body mechanics, and we see the familiar cotangent formula being used to find the principal stresses, but flipped as a tangent. Next, suppose we took a sample of correlated datasets such as people's weight and height. We can label these pairs of data as x and y. In one dimension, sample variance is a very useful quadratic measure of spread. For 2 dimensions and beyond, we can define a generalization of it called the covariance. The covariance matrix is analogous to what the Hessian is for the second derivative. Then perhaps it's not too surprising that we can come up with 2 uncorrelated variables by a simple rotation. This is called the principal component analysis in statistics. Another major challenge for mechanical engineering and physics students is understanding general rotational motion. This one, I don't even want to dive into the mathematical details because of its complexity, but it should rhyme with what we have been doing so far. Every rotational motion of a rigid body can be decomposed into rotations about its 3 principal axes, no matter how asymmetric the shape is. First axis with the smallest moment of inertia, the third axis with the largest, and the intermediate axis. We front-loaded all the results and applications, and saved all the juicy mathematical details. The Hessian and linear transformation are different types of objects, although we choose to represent both with matrices, which is the main source of confusion. Let's start with vectors and covectors, which are tensor rank 1 objects. Vectors are just vectors. Covectors are linear functions that take a vector and outputs a scalar. And as per what linear means, it obeys additivity and scalar homogeneity. And we do have a meaningful way to distinguish them in matrix algebra notation. Vectors as columns and covectors as rows. So covectors naturally act on vectors to output a scalar. Now, as per linear transformations, they eat one vector, then output another. And 0-2 tensors consume 2 vectors to produce a scalar. In matrix notations, linear transformation is matrix acting on a vector to give another vector. And when it comes to 0-2 tensors, matrix notation isn't the best at capturing what's actually happening. To make matrix multiplication work, we have to artificially transpose one of the vectors, but it's important to note that the row vector isn't actually a covector. If the matrix represents the Hessian, this quantity is the mixed second directional derivative with respect to each vector's directions. So in matrix notation, we have to rely on the context to distinguish different types of tensors. But there are other notations out there that has the context built into the notation. But for this video, we're gonna stick with matrix notation for a good reason. Next, let's understand what it means for a tensor to transform like a tensor. This vector can be represented as an array with 2 and 2 for its entries, which means it is 2 times the first basis plus 2 times the second basis. But we can choose to work in a different coordinate system, where the same vector is now described as 1, 3. We can write a matrix P, where each column represents the new basis in terms of the old basis. So the first column is 1, negative 1, and the second column is 1/3, 1. Now, to transform the old components to new components, we have to multiply by P inverse. As per why that is the case, if you change your measurements from yards to feet, then your basis shrinks by a factor of 3, but your component grows by a factor of 3. So your vector components vary inversely with respect to how the coordinates change. As per a 2-dimensional example, if you rotate your body clockwise, then it's as if the world is rotating counterclockwise with respect to you. Now, let's describe how linear transformations change with respect to change of basis. The vectors x and y change description to x bar and y bar in a different coordinate system. And we want to describe the actual transformation A in this new coordinate system. So we will make couple of substitutions, then multiply by P inverse on the left side. And this triple matrix product describes the same linear transformation in this new barred coordinate. Now, as per rank 0-2 tensor, we first write what the tensor does to 2 vectors. Then make the substitution, and distribute the transpose. This matrix triple product is how a rank 0-2 tensor transforms under change of basis. Let's take a look at this quadratic function in 2 dimension, and the tensor here is the quadratic tensor, which represents the coefficients of the quadratic function, and it would be half the Hessian. Now, let's apply a change of basis so that our quadratic function is written in a different coordinate. You can work out the distribution on the left side or the matrix multiplication on the right side, but the answer should come out the same. Now, if we take the same matrix and transform it like rank 1-1 tensor, then it stays the same under any change of basis, as the identity transformation should leave every vector unchanged regardless of the coordinate system. So this clearly shows that rank 0-2 tensors and rank 1-1 tensors transform very differently under a change of basis. There is one more case, the stress tensor, which is a rank 2-0 tensor. We can think of it as a multivector, where a different vector is associated with each direction. In order to see how it transforms, let's first understand how a covector transforms. Covector eats a vector to spit out a scalar. And no matter what coordinate we choose, it should output the same value. So let's throw in a P inverse, which is the identity. Since P inverse x is x bar, alpha P has to equal to alpha bar. So a covector transforms the opposite way a vector does. As per a well-known example, the change of variables for derivatives using the chain rule and for integrals with substitution vary in opposite directions, and the matrices of transformation are inverses of each other. Now, as for how a rank 2-0 tensor transforms, I'm just gonna wave my hand and make a heuristic argument. Rank 1-1 tensor has columns that transform like a vector and rows that transform like a covector. Rank 0-2 tensors have rows that transform like a covector and also columns that transform like a covector. So we have to artificially flip the orientation of the transformation. So for a 2-0 tensor, columns transform like a vector and rows also transform like a vector. So we have to make an artificial transpose. If you're not satisfied with this argument, the best argument that does not involve index gymnastics is to think of 2-0 tensor as a function that eats two covectors to spit out a scalar. Very much like how a vector is a function that eats a covector to spit out a scalar. And the proof is left as an exercise. We have now explored every type of rank 2 tensors and their transformation rules under a coordinate change. And in general, they transform differently. But there is a special class of transformations called orthogonal transformations. Geometrically, these are rotations and reflections. Algebraically, they are matrices whose inverse is equal to their transpose. So, under any coordinate change made of rotations and reflections, every rank 2 tensor transforms the same. Now, the spectral theorem says that we can apply a change of basis with some specific rotation or reflection to a symmetric tensor to diagonalize it. Although a rotation is sufficient not only to diagonalize a matrix, but also order the eigenvalues in increasing order. To see this in action, let's pull out our right hand and identify our orientation. Now, for any rank 2 tensor, we can find our eigenvectors and order them in increasing order with respect to their eigenvalues. But with this specific choice of eigenvectors, we can't simply rotate our hand to put it in correct orientation. But eigenvectors don't give a flip about your choice of orientation. So it's always possible to diagonalize our rank 2 tensor with simple rotation. The spectral theorem is strictly about the orthogonal diagonalizability of linear transformations. The principal axis theorem is the generalization to any rank 2 tensors. And these concepts truly showcase the universal applicability of linear algebra. Additionally, these linear algebra concepts generalize remarkably well to infinite-dimensional function spaces. As long as the underlying principles are linear, we can develop infinite-dimensional analogs. And they will be addressed in future videos.